Alright, so in this review session, I'll be discussing NBR, IND, and REC, these three modules. And I'll just go over the main concepts in these three modules. Now, as far as these three modules are concerned, it is more important for you to understand the concepts and the theoretical concepts behind these modules rather than the syntax itself, because there's no new syntax introduced in these three modules. So I'll be focusing in this review session mostly on uh, the concepts that are required, that are covered in this one, and those will be useful to you in the finals. Alright, so with that, let's get started. So I'm going to make my notes at the bottom of notes 17, just so you know. So I hope everyone can see this. So let's start with NBR, the numerical representations. Now this is a very important topic in its own right, especially for people who do a lot of scientific and numerical computing, because the quality of the computations depends directly on how accurate they are, and due to the limitations of size of memory of the computer, you can't make your computations exactly accurate. To give you a simple example of like a broad overview of the issue here, consider how you would represent say an irrational number, say like pi. Now we know the decimal representation of it to a few thousands or maybe even millions of digits, but no matter how many digits we use, we can never represent it exactly in the decimal format, which is why we invented a new symbol called pi for it. So on a computer, what happens is exactly the same thing, except it happens for even other numbers, not just irrationals. So because of the limitation of the size of the memory, you can represent numbers using only a finite amount of space. So you necessarily lose some precision. You cannot represent numbers arbitrarily precisely. And that leads to a whole host of issues which we'll see in this module. So, so let's start with number representations, specifically how you represent a given number in different number systems. So we have the decimal number system, which is your normal number system where you have the 10 symbols 0, 1 all the way until 9, and you represent a number. So these are your symbols, and you represent a number, say in powers of 10. So use powers of 10. So for instance, a number like 719 is basically a shorthand way of writing 7 into 10 raised to 2 plus 1 into 10 raised to 1 plus 9 into 10 raised to 0. So you already know this. Now this exact same representation can be done in other using other bases, and the base that's used in computers is the binary. So in binary, as the name suggests, you use only two symbols, 0 and 1, and you use powers of 2. So here a number say 1100 will be, in exact analogy with how we did the decimal expansion, would be 1 into 2 raised to 3 plus 1 into 2 raised to 2 plus 0 into 2 raised to 1 plus 0 into 2 raised to 0. So, oops, here we go. So, in our regular decimal notation, this number corresponds to simply 8 plus 4 plus 0 plus 0, which is 12. So, as you can see, you can represent numbers in different bases and different symbols in different ways. Now, the same holds for decimal fractions. Supposing you had 719.3 here. So that would correspond to just 3 into 10 raised to minus 1. So you use negative powers after a decimal point. In the exact same way over here, if you have say 110.1, then you would have over here as 1 into 2 raised to minus 1. So that would correspond to 0.5, which means this will be 12.5. So this is basically it. I mean, so what this tells us is that you can represent numbers. The representation of a number is distinct from the number itself. The number 12 or 12.5 or 719.3 represents something concrete, but the representation, the way it's represented in different number systems is different. And so in binary it looks as a series of ones and zeros. In decimal system it will look at something else. In hexadecimal it will look at something else. So this is the way you represent numbers in different number systems, and the binary number system is the one that's used in computers. So now let's look at what we understand by finite number systems. Now there was a question about this on Piazza and about this, and it seems like this is not entirely still clear to all the students, so I'll just spend a few minutes going over it. So let's take the prototypical example of a finite number system, the 3-digit base 10 system. So once we understand how this simple system works, we'll be able to understand the more sort of complicated looking IEEE double format and be able to answer more complex questions like what's epsilon and what's real min and all those things. But before that, we'll first focus on understanding 3-digit base 10 system. Now, it's base 10, so it's familiar to us because we use the decimal system already. 3-digit means that you represent any number in terms of 4 symbols. So A, B, C, and E. Okay. So what this means is basically this corresponds to the number A point BC into 10 raised to say E minus 4. Okay, so this is the definition of the representation. ABCE corresponds to number A point BC into 10 raised to E minus 4. Okay, so each of this A, B, C, and E can take A, B, C, and E can take values from 0 to 9. Okay, so for example, if you have the number say 1, 2, 3, 4, that would correspond to the decimal number 1.23 into 10 raised to 4 minus 4, which is simply, I meant into over here, which is simply 1.23 into 1, which is 1.23, right? So the representation of 1.23 in this number system is just simply 1, 2, 3, 4. The problem with allowing A, B, C, E to take any values from 0 to 9 is the following. We immediately run into a problem when we allow A, B, C, and E to take independently any value from 0 to 9. If you look at the number, say 0.05 into 10 raised to 5, okay, now this number has the representation of say 0.05, and then the exponent will be 5 plus 4, 9, right? So this number has a representation 0.059, but this number can also be written as 0.50 into 10 raised to 4. Yeah. So this number would then be represented as 050, and now the exponent will be 8. Similarly, this number can also be written as 0.500 into 10 raised to 3. And so this number would have the representation 5007. So clearly we see there's a problem here because the same number has got three different representations. In other words, the representation is not unique. So this is not a good representation. We would like to have a unique representation for numbers. So to circumvent this problem, we require that, so to prevent such non-uniqueness, we require that when a equal to 0, e is 0. So that immediately rules out the first and the second representations, because in both of these cases the first digit, which is a, is 0, whereas e is non-zero. So therefore the first two are not valid representations, and the only valid representation is the third one. And so we sort of work around this problem and make a unique representation for every number. So this is the additional rule we need to make sure that this is what we call a good representation, meaning that every number has a unique representation. Now let us look at some of the characteristics of this finite number system. Clearly, being a 3-digit number system, you can represent only a few real numbers and not all of them in this one. For instance, I can never represent a number 1.2345678910910, or not 910 but 9, say. So I can never represent a number. I cannot represent a number like 1.2345 exactly in this system. Why is that? Because it allows only 3 digits at the most. So I have to, so to represent a number like this, say 1.2345, I have to represent it as something which is closest to it. Okay. So let us look at what are the possible numbers, how many numbers can represent in this system. And that's a very simple calculation. I won't take the route which was explained in the lecture notes, but I'll show you a slightly different way of understanding that, which will also tie in with the other advanced concepts in IEEE. So if you look at this number system, so question is, how many numbers can you represent in this number system? So let's look at that. So we have A, B, C, and E. Now we said that each of these A, B, C, and E can take any value from 0 to 9, with the exception that when A is 0, E must be 0. So let's consider two cases. So when A is 0, B can take any value from 0 to 9, C can take any value from 0 to 9, and E can only take the value 0. So what are number of possible numbers of this form? We have one choice for A, 10 choices for B, 10 choices for C, and only one choice for E. So that gives you 100 numbers. Next, let's look at the non-zero values of A. So when A takes any of the values 1 to 9, B can take any of the values 0 to 9, C can take any of the values 0 to 9, and here E can take any of the values 0 to 9 as well. So here the number of such possible numbers is 9 for A, 10 for B, 10 for C, and 10 for E. So that gives you 9,000. So the total number of representable numbers in this finite system is simply 9,000 plus 100, 9,100. So this shows us that only 9,100 real numbers can be represented in this system. And as you know, there are infinitely many of them. So obviously you cannot represent all of them. And that illustrates one of the limitations of a finite number system. Now you must understand that this is exactly the same limitation that is faced by computers when storing any real number. They have more than 3 digits, that's for sure, but they still cannot represent every single real number out there. And this is simply because they have only so many digits. And we'll come to those limits exactly when we talk about the doubles. So for now, this simple example, you can see that you can represent only 9100 real numbers and not every single one out there. Okay. Um, so that's number one. So for instance, as I said, you cannot represent a number like 1.2345, or you cannot represent a number like 1 by 3. So this actually is a problem even with our regular decimal system. If you look at a number like 1 by 3, this is actually 0.3333 recurring, right? But you will never be able to represent 1 by 3 exactly with a finite number of digits in the decimal number system. So this is not like, this is a common problem with any number system. If you have a finite number of digits, you cannot represent all real numbers that are out there. Okay, so this is similar to the problem of representing 1 by 3 in decimal with a finite number of, anyway, this is, let me not waste valuable note space in that because I might have to delete it. So so the point is that this is not this is a fundamental limitation of finite number systems, that since you are limited to the number of digits, you cannot represent every single real number out there. The other thing that is a consequence of the finiteness of the number system is precision. So let's answer the question of precision. Okay, so let us look at, say, one of the numbers in this representation, say 1248, okay, which corresponds to 1.24 into 10 raised to 8 minus 4, which is 1.24 into 10 raised to 4. Okay, so what is the next largest number that you can represent in this system? It is clearly not 1249, because 1249 will make it go up by a power of 10, but it is 1258, okay, which corresponds to 1.25 into 10 raised to 8 minus 4, which is 1.25 into 10 raised to 4. Okay, so this is the next largest number you can represent in this number system. After this, you can try increasing the other numbers, say A, B, and E, but none of these numbers will be smaller than this one. So you see that you're not able to represent any number between 1.24 into 10 raised to 4 and 1.25 into 10 raised to 5. So the difference here is 0.01 into 10 raised to 4, which is 100. So in this interval of 100 from 1.24 into 10 raised to 4 to 1.25 into 10 raised to 5 into 10 raised to 4, you're not able to represent any number. And that is what I mean by precision. So the precision is 100 here, which means that you can represent numbers only up to plus minus 50, right? So if you want to represent any number between this one, you'd either round it up to 1.25 into 10 raised to 4 or down to 1.24 into 10 raised to 4, depending on whether it's closer to this number or this number, right? So that is another consequence of finite number systems, namely that you cannot that it has a finite precision. You cannot be arbitrarily precise. That is kind of related to the fact that we cannot represent all numbers, because if we are able to represent all real numbers out there, then the precision would be infinite. The fact that we're not able to represent all real numbers means that it must have finite precision. So let's look at this question of precision a little more precisely. So let us look at what is the precision. Now this precision that we found here, 100, clearly depends on what number you're looking at. In other words, the precision at a given number is a function of the number itself. And I'll explain what I mean by that. Consider a general representation, say A, B, C, E. Oops, E. Okay. So the next higher representable number after that would be simply A, B, C, C plus 1 and E, right? Just as 1248, the next one is 1258. So ABCE is ABC plus 1E, right? So the difference between the two, So the difference between these two will be simply 0.01. So actually let us look at the what these numbers correspond to. So ABCE corresponds to A point BC into 10 raised to E, and the next higher representable number from this one is ABC plus 1 E, which corresponds to A dot B C plus 1 into 10 raised to 10 raised to E, right? So the difference between the two is simply 0.01 into 10 raised to E. And since 0.01 is, oh, never mind, this is E minus 4. I knew I was missing something. So both of these are E minus 4, because that's how we define the representation. So the difference between the two is 0.01 into 10 raised to E minus 4, right? And since 0.01 is 10 raised to minus 2, you can combine the two indices using the laws of indices, and this will be 10 raised to E minus 6, right? So what does this tell us? This tells us that, so this is the measure of precision. So this is the range of numbers that have to be either rounded up or rounded down to be representable in this system. So what does this tell us? This clearly tells us that as E goes up, the precision goes down. As E goes up, the difference goes up, right? If E is 1, then it's 10 raised to minus 5. If E is 5, then the difference is only 10 raised to minus 1. So as E goes up, difference goes up and precision goes down, right? So this is the first characteristic, that the precision at any given number in the representable numbers depends on what number you are at, and specifically on the exponent. So for example, the precision at 1004 is 10 raised, so let's look at what 1004 is. 1004 is 1.00 into 10 raised to 4 minus 4, which is simply 1. So the precision at 1, the number 1, is, or the difference, which is the inverse, is just, so the difference between 1 and the next higher representable number, which in our notation we call EPS. So I'll just introduce it right now, but we'll look at it in more detail later on. So EPS1 in this number system is simply 10 raised to E minus 6. So E is 4 here, right? So 4 minus 6, which means 10 raised to minus 2, which is 0.01. So this is how you compute the precision at a given number, and as you see, it's clearly a function of where you are in number, specifically the exponent. Now you have to be careful when you compute the precision this way. So this holds for either plus or minus, both ways it's the same. But you have to be careful when you're at specific numbers. So for instance, if you're at a number, so warning, say your C is equal to 9, right? If C is equal to 9, then you can't do C plus 1, because C plus 1 will be 10, and so that would correspond to increasing the exponent E. So when C is equal to 9, so let's take an example. Say 999E, okay? So where E could be anything, say 9995. So that corresponds to 9.99 into 10 raised to 1, right? The next higher representable number in this one would be simply 1.00 into 10 raised to 0, right? Which corresponds to, so this number corresponds to simply 1006, right? So here the precision is also the same as what you would have calculated by the above formula, namely the precision, the difference between the two is simply Is it 10 raised to, yeah, 10 raised to 1, and this should be 10 raised to 2. I'm sorry. All right. So the difference here between the two would be simply point, um, let's see. So 10 raised to 2, so 0.99. So this is 1 minus 0.999. So let's see. Difference is 1 minus, or 10 minus 9.99 into 10 raised to 1, which is 0. Oh, sorry, 1 point, no, 0.01 into 10 raised to 1, which is 10 raised to minus 1, which would be the same as what you would have done if you had directly done e minus 6, 10 raised to e minus 6 for 9995. So it works for c equal to 9. But if you have a number, so this is okay. So this one is okay. But if you have a number, say, like 1004, I already taken that, so 1006, say, which corresponds to 1.00 into 10 raised to minus 2, 10 raised to 2. I've already done 1006. Okay, let me take 1003. So that corresponds to 1.00 into 10 raised to minus 1. Okay, and if you go one below it, the number which is one below it would be simply 999 and 2, which corresponds to 9.99 into 10 raised to minus 2, right? So the difference between these two numbers is simply 1 minus 0.999 into 10 raised to minus 1, which is, so the difference is 0.001 times 10 raised to minus 2, so that is 10 raised to minus 5, right? So here you see that the formula doesn't work, because if you did simply over here, so the exponent here is 3. If you did 3 minus 6, you'd get minus 3, but here the difference is actually minus 5. Let me check the calculations just to make sure. Oh, here we go. Yeah, so if you did minus 1 minus 6 here, you'd get minus 7, but the difference is actually minus 5. So only in these edge cases, when the exponent rolls over, you cannot apply this analysis. So here in this analysis, we have assumed that e doesn't change when you go from c to c plus 1, or when you go from c to c minus 1. But in edge cases like this, when the e actually changes, you have to be a little bit more careful to figure out what the precision is. Okay, so with that caveat, you can do the precision, the epsilon analysis, in this way. So uh, 1.00, oh, something wrong, so this must be 4. Okay, so anyway, the point is the formula doesn't work here, because you have minus 1 minus 6 will give you minus 5 here, whereas the difference is minus 4. Okay, so in this second case, you have to be careful. So here you cannot use e minus 6, okay, as the precision. Difference equal to 10 raised to e minus 6. So so the precision depends on the number you're looking at, specifically the exponent of the base. Now, some consequences of this precision, this finite precision, is that your computations are never exact, and you have done in the assignment. I don't know why the hell am I raising my own hand. So in the assignment, you have done examples. You've done a problem where you've seen that simple arithmetic identities like a plus b plus c is actually not equal to A plus B plus C, right? And the reason why that happens is because A plus B may itself not be a representable number, so it is rounded up or down to the nearest representable number. And then when you add C, again it may or may not be a representable number, so it's rounded up or down. And the same thing goes on over here. If you do B plus C first, it may, if it's not a representable number, it will be rounded up or down. And then you add A, and again it may not be a representable number, so it will be rounded up or down, and so the net result may not be equal to each other. And so simple arithmetic identities like these do not work. And we have seen some examples in the assignment. So this is necessarily a consequence of the finite precision of this finite number system. And this is true of any finite number system you take. I've illustrated it for the simple one, this prototype model, but this is true for every finite number system. All right, so let's move on to the real finite number system that we deal with in computers, namely the double. So IEEE floating point double. Okay. So this is essentially in its essence, it's the same as what we have been doing so far, this finite number system 3-digit base 10. The only difference is that instead of 3-digit, it's a 52-digit base 2 number system. So the number of digits have increased considerably, and the base has changed. But in a sense, it's the same. There are a few minor things, a few sort of technical details that the IEEE system does to kind of maximize the representation we can get out of it. So notice that one of the problems we had with our earlier number system, the 3-digit base 10 number system, was that we couldn't allow E to take non-zero values when A was 0. So in a sense, we declared a whole range of representations as invalid because it would lead to non-uniqueness. So the way IEEE gets around that is that it defines 3 kinds of numbers. Okay. So the first one is what is called the normalized numbers. The second one are the unnormalized numbers, and the third one are special numbers. Okay, and by doing this, we are able to basically use all the possible representations to represent some number, and so maximize the numbers you can represent in this number system. So in this IEEE system, you don't have to limit yourself to E not taking certain values when the digits are so and so. Okay, so first let's look at the layout of how these numbers are represented. So numbers are represented in the double format. They are 64-bit, which means there are 64 digits. So bit is the equivalent of digits in the binary number system. So you have 64 of 0, 1s, and so on and so forth, of which the first bit is the sign bit, which tells us whether the number is positive or negative. The next 11 bits are the exponent bits, and the remaining 52 are what is called the fractional bits, or the mantissa or significant. There are different names given to it. So there are 11 bits devoted to the exponent, 52 to the fraction, and 1 to the sign. Okay. Now let us look at what these normalized, unnormalized, and special numbers are. So right off the bat, since this is a binary number system, the number of digits, the number of values that the exponent can take, so you have 11 bits to fill, right? 11. So let's look at the number of values you can take. So sign. So sign is 1 bit. It can be either 0 or 1. So that is taken to mean 0 means positive number and 1 means negative number. Okay, so only 2 values for sign, 0 or 1. 0 means positive, 1 means negative. The exponent can take 0 or 1 in each of the 11 places, right? So it can take 2 raised to 11 values, okay, starting from 0 all the way until 2 raised to 11 minus 1, which is 2047. So it can take values, integer values between this range, 0 to 2047. Okay. Now, if we, so remember, as we did in the finite number system, we represented a, b, c, e as a point b, c into 10 raised to e minus 4. The reason we did that is to allow for negative exponents of 10. In the exact same way, we would subtract something from e to allow negative exponents of 2 so that we can represent numbers which are less than 1. And I'll come to that in when I discuss normalized and unnormalized numbers. But the number we subtract from e is basically minus 1023. Okay, so the effective range of e is basically from minus 1023 to 1024, if you will. Okay, so actually let's not write that, that might be confusing. So we just subtract 1023 from this one to represent negative exponents as well. And finally, the fractional bit has 52 bits. So again, it can take 2 raised to 52 values. And whatever that number is, I don't remember in decimal. But so it can take these many values. Now let's look at what are these three kinds of numbers that IEEE deals with and how it circumvents this problem of non-unique representations. Okay, so the first kind of numbers are what we call as the normalized numbers. So what are normalized numbers? They're essentially numbers of this form. So you have minus 1 raised to s times 1 point, so the fractional bits f1 all the way until f52 in binary. Okay, so I'll just write binary over here like that, times, let me just space it out a bit so it's more clear, times 2 raised to e minus 1023. Okay, so these are our normalized numbers. Now what does this tell you? So this is, so a number, a 64-bit number, normalized number, has the corresponds to the value given by this formula I've just written down, minus 1 raised to s times so and so. So s is, if s is 0, then minus 1 raised to 0 is 1, so it's a positive number. If s is 1, then minus 1 raised to 1 will be minus 1, so it is a negative number. So this gives the sign correctly. Now this f1 up till f52 are those 52 bits in this 64-bit representation. So we don't store that 1 explicitly, it's implicitly assumed that it's going to be 1. Okay, and then you multiply that with a exponent of 2, just as we did in our finite number system with 10 raised to e minus 4. So this is what corresponds to a normalized number. Now note that all of these numbers are necessarily more than 1. You'll never be able to denote 0 in this number system. And why is that? Because the fractional part starts with a 1 point something. No matter how big this 2 raised to e minus 1023 is, as long as it's finite, it will still be some non-zero value. So you can never represent a number like 0 in this system, in the normalized numbers. In other words, 0 is not a normalized number. So that is where the unnormalized numbers come in, and their representation corresponds to this formula. So it's exactly the same, almost entirely the same as the normalized numbers, with the small difference that instead of 1 you have 0 point f1 all the way until f52 in base 2 times 2 raised to minus 1022, oops, minus 1022. Okay, I'll come to special numbers in a second. So here the range of e for normalized numbers corresponds to, so e can take values from 1 to 2046. Okay, so these are the allowed values of e for normalized numbers. For unnormalized numbers, e is essentially equal to 0. So here you can see that we can represent 0. How we can represent 0? By just making all of these 52 digits of f 0. So these correspond to what are called unnormalized numbers, which are numbers in the range 0 to 1. Maximum value is just less than 1. It can never take the value 1 again over here because of this exponent over here, right? And finally, the special numbers are those which correspond to e equal to 2047. And here you have three cases. So if all the fractional bits are 0, so F1 all the way to F52, all of them are 0. So F1, F2, F3, F4, all of them are 0. Then that that corresponds to either plus or minus infinity. So if S equal to 0, then that means it's plus infinity, and if S equal to 1, it means it's minus infinity. Okay. The next case is when they are non-zero. So when F1 all the way to F2, so I'll just say otherwise it corresponds to not a number. Okay, so not a number, as you can see, has many different representations, and all of them correspond to not a number, because F1 to F2, F52 can take any value except all 0. So there are many different ways you can represent not a number, but infinity and minus infinity have a unique representation. So this covers the three categories of numbers that the IEEE system defines. We have the normalized numbers, the unnormalized ones, and the special numbers. So with this, you can see that we are allowing all of these numbers, the S, E, and F, to take all possible values they could without restricting any of them, like we did earlier in the three-digit base 10 system. And we are able to extract the maximum representation out of the given bits. So this is the IEEE floating point double standard. Now, so the way it works is that when you're given a 64-bit number, you look at E. The value of E will tell you. You first look at E to tell you whether it's a normalized, unnormalized, or special number. If E is anywhere between 1 to 2046, it's a normalized number, and then the value corresponds to formula number 1. If E is equal to 0, then it's an unnormalized number, and the value given by that number corresponds to formula number 2. And if E is 2047, then the formula corresponds to either A or B. So either it's infinity or minus infinity or not a number. Okay. And note that I'm writing E in decimal here, but E will be E will be in binary. So E equal to 2047 will correspond to 11111111 times in binary. Okay. Similarly, E equal to 0 will correspond to 00000 in binary. Okay. So if E is neither of these two values, then it's a normalized number, otherwise it's a normalized or special number. Okay. Now so again, the same the same concepts that we discussed for the three-digit base 10 system apply here, namely the concept of precision and the concept of how many numbers you can represent. Now obviously the number of numbers you can represent here is much higher than what we could earlier, because we have more digits to play with. So instead of 9100, the number of numbers you can represent is tremendously large. It's given in the PDF, so I won't repeat the numbers here and bore you. But not only is the precision very good, it's much better because we have 52 digits now. The number of representative numbers is also very large. They are sort of consequence of each other. But two or three important things to remember here are, which carry over from our earlier discussion, is this concept of EPS, the epsilon of R. So if R is a number, epsilon of R is simply the next higher representable number after R. Okay. So you compute it in the exact same way as we did in the case of the 3-digit base 10 system, where we just looked at the number and then we looked at the next high representable number and then computed the difference between the two. And that is what gives you EPS of R. In particular, there is EPS of 1, which is called real min. It's given a special name, which is the next high representable number after 1. And there's another thing called real max, which is the maximum representable real number in this number system. So the values for these are given in the lecture notes, and I encourage you to see them and try to derive them for yourself. Very simple computations involving sums of geometric series, and these three are basically like called special names because they sort of represent the limits of representation of this number system. And so that's that's all I had to say as far as um, the IEEE number system goes. One thing to note here is that in the in the in the binary digit, sorry, in the 3-digit base 10 system, we said that the the difference between the number and the next higher one usually is 10 into e raised to minus 6. Let me just bold that over here. So it's 10 into e raised to minus 6. So here the fs of r is usually, let me write that in capitals so you remember, is usually whatever the power of 2 is. So supposing it's a power of 2 raised to e, so 2 raised to e minus 52. Okay, note that e is not the same e as this. This is the e in the IEEE representation. This is the actual power of e that the number is. So this small e is basically capital E minus 1023 for normalized numbers, and for unnormalized it's minus 1022. Okay, so that's how you get the difference between a number r and the next one. Obviously, as I said earlier, if you're at an edge case like the ones I illustrated earlier, then you have to be a little bit more careful in computing the difference. So I think that's all I have to say for NBR, and let me move on to the next module, IND. Oh, this is becoming a long discussion. So as far as IND and the next module REC is concerned, so you must remember all of these three modules, there is like very little sort of new MATLAB syntax or new MATLAB specific uh, concepts to learn. These are topics which are highly conceptual, and you must understand them sort of on a theoretical basis to be able to answer questions in the exam. So I'll be discussing mostly and only theory in this one because there's very little in terms of new syntax or new MATLAB tricks to learn in this one. Okay, so let's look at the induction module now. So in induction, here's the basic idea. The basic idea of induction is the following. So supposing you're given some statement involving a positive integer n. Okay, let's call that s of n, statement of n. Okay, so the way you apply induction is in two parts. The first one is you first say verify if s of 1 is true. Okay, and secondly you verify that if s of k is true, then s of k plus 1 must be true. Okay, so if you verify statements 1 and 2, damn it, I can lose my hand. So if s of k is true, then s of k plus 1 must be true. If you can verify both 1 and 2, then you can say that s of n holds for all positive integers. So this is the basic sort of inductive hypothesis, inductive principle. Okay, now there's a sort of a trivial generalization of this in the sense that there might be some statements which hold for not all positive integers, but say for all integers starting from 5. So in that case, instead of verifying that s of 1 is true, you would verify if s of 5 is true, and then do the second step. If s of k is true, then s of k plus 1 must be true for k greater than 5, and then it would hold for all integers more than 5. So this is like a trivial generalization of the inductive principle. Instead of saying for all positive integers, you would say it would hold for all integers greater than 5. But the basic idea is this. You have to verify s of 1 is true, and then if s of k is true, then s of k plus 1 must be true. So the key step to watch out for, most of the key things the key sort of mistake or the key um, place where people make a mistake is after verifying S of k is true, S of 1 is true, and you show that S of k is true and S of k plus 1. These steps are usually not that difficult, but you must also verify in your head whether it makes sense to go from 1 to 2, from 2 to 3, from 3 to 4, and so on and so forth. So, in other words, just like do a simple sort of verification to do the inductive step, the second step, for 1, 2, 3, 4. Like just do it for the first few integers, and then you can do the general step. Okay, so this is a very common mistake people do where they just do S of 1 is true and then somehow show that if S of k is true, then S of k plus 1 must be true. But it can very easily lead to false conclusions. And in the past exams, you've probably seen, I think on Piazza I saw a post where somebody had shown how in one of the past exams there was a problem where the induction hypothesis failed. So just watch out for that. There are some good problems where the induction hypothesis fails if you're interested to look at in the book by Apostle called Linear Algebra and Calculus, I think. So it's some good discussion on induction and why it fails and how it fails. So that's the basic idea in induction. You just show the base case. So this is like the base case, if you will, and I'll use this concept of base case. It's more relevant for recursion, but I'll just use it here as well because I can't find a better terminology. This is sort of the base case of induction, and then this is the inductive step. So that's the basic idea in induction. So you start off with 1, show that holds for 1, which is usually very trivial to prove, and then do the inductive step. On the other hand, in recursion, so let's look at what recursion is. The basic idea of recursion is when a function calls itself, okay, within its body. So like you have some function f, say y equal to f of function, damn it, here we go. So function y equal to f of x, and then you do something in the body, and then you somewhere say call z equal to f of w, okay, and then do something more and n. So this step is the recursive step where you're calling the function f within the body of this same function f. Okay, so the most important thing for you to understand in recursive functions is that you must have some sort of a terminating condition. So if you will, it's similar to a while loop, and a while loop keeps on executing until the condition becomes false. So this is not exactly a while loop, but it is like a while loop in the sense that you keep on calling the function within itself, and there must be some way of getting out. Just as in the while loop you put a condition that when it becomes false it must get out, so over here you need some condition for it to terminate recursion, and that is what we call as the base case. So the base case, this is the most important thing. So whenever you start thinking about a recursive function, the most important sort of one of the most important first step is to identify the base case. Okay, and this is in the base case, so which is basically the case when you can compute the answer directly. So here you return the answer directly without calling the function itself. So if you don't have the base case, you'll have sort of an inception kind of situation where it's a dream within a dream within a dream. So it's a function within a function within a function within a function, and so on and so forth. So it's very important, and this is probably the most important step that many people make a mistake with, is that you need to start with the base case. You must identify what the base case is and return and define the output for the base case. So you must always have a base case over here. So the first thing you check over here, usually, not always, but usually the first thing you check is if it's the base case. And if so, then you do something and then return something. Okay. So you set return, so you set y equal to something and return. Okay. And then If the base case is not satisfied, then you do your else. Okay, so this is the most important sort of construct. Like you must identify the base case first and return the answer directly without calling that function. That is what the base case means. You do not call the function again recursively. And then otherwise you just call it again and keep going until you hit the base case. So it's important to identify the base case correctly. You must ensure that at some point during the recursion you hit the base case. So like if you're calling, you did examples in the recursion module. We did Sudoku, for instance, or even the induction one. So where you did the Pascal's triangle. So the base case there was when you reduce the rows, at some point you would hit row equal to 1 or you would hit column equal to 1. So that is the base case. You must ensure that somehow you are hitting the base case no matter where you started. Otherwise you have an infinite loop. Similar to what you would have in a while loop if you don't have a condition that becomes false at some point. So that is the main thing to understand about recursion. Um, Other than that, there is nothing, again, there is no new MATLAB syntax to learn in recursion. Um, so I mean, that's all I have to say about recursion. Now I'll take questions if you have them.